Section 10.5 is going to discuss how to find the area of a region in polar coordinates. To do that, I'm going to have to remind you of a formula you haven't used since trig class. We're going to look into trying to find an area of a little sector. So two angles bounded by some function in polar coordinates. We want to find this area. Now back in Calc 1, what we did was we divided up into small vertical strips. We added up the area of each of those vertical strips. That became a Riemann sum. And we let those vertical strips get really, really small. The limit became the Riemann integral. And we found from Newton's theorem that we could find the antiderivative and get a nice quick answer by evaluating the expression at the limits evaluated with the antiderivative. Well, here we're going to do something similar, except instead of dividing it up in nice vertical columns, we're going to divide it up into these little almost rectangles. And to help us calculate the area of these things, let me remind you of a formula, like I said, that you haven't used since trigonometry, and that is the formula for the area of a sector. So each one of these things we can kind of regard as a sector, if we kind of round it off a little bit and use a little bit of imagination, and especially if these become really, really small, then the approximation to a sector gets quite good. So that formula for the area of a sector is this: 1/2 theta times r squared, where theta was in radians. Great. The upshot of this is when you do all the work and you calculate the limit as these sectors get really, really small, you get something like this. And then you end up with the formula that we need, which is the area in polar coordinates. Basically, it's the 1/2, which comes from our area of a sector formula, times the integral from alpha to beta of your r squared, or in this case, f of theta. Same thing. So that's it. Let's go ahead and try and find the area of a few of these things. And we'll start out with problem number 16-ish. 16-ish. And that is, let's find the area of the leaves in this 4-leaf clover. Now we spent a little time in section 10.4 trying to understand some things about how these are generated, where their axis of symmetry is, etc. And we're going to get some payoff from that right now. So we're going to try and find the area of all 4 of these, but it's enough, I think, to just find the area of half of one leaf. Why can we get away with just half of one leaf? What would we do? Yeah, multiply it by 8. Double it, and you get one leaf. Times by 4, and you get all of them. So essentially multiply it by 8. So it's enough just to figure out this one little piece here. Now, I think we went over a formula to find the axis of symmetry here in section 10.5. And that axis of symmetry was, let's see, theta equals pi over, what was it, 2n? No. Yeah, 2n. 2 times 2 in this case, so in other words, pi over 4. The graph of a sine function like this starts out at 0. So what we've come up with is our limits. Our limits are going to go from 0 to pi over 4. And then we're going to integrate this squared. So that's where I'm going to begin my calculation. But do you understand our plan? Okay. So let's do 1/2 times the integral from 0 to pi over 4 of 6 sine of 2 theta squared d theta. Six squared is 36 times 1/2 is 18. So let me pull that out front. 18 times sine squared of 2 theta, d theta, between 0 and pi over 4. How are we going to integrate sine squared of 2 theta? Oh, man, that's like a couple months ago we did that. You don't expect us to remember that, do you? Power reduction formulas? Ring your bell to anybody? 18, 0 to pi over 4. That's going to be 1 minus cosine of what? It's going to be twice that angle, so 4 theta. And so we can clean this up a little bit more. The 2 and the 18 are going to cancel. And now we're stuck trying to find an antiderivative. 1 minus cosine of 4 theta d theta. Or better yet, 9 times theta. I'm going to have to divide by 4. And I know I'm going to need a sine of 4 theta. But do I have... Is this sign correct? Should it be a minus or a plus? It's going to stay a minus. Because when you differentiate sine, you're going to get cosine. So we don't have to change the sign here. All right, so plugging in our limits, I get 9 times pi over 4 minus sine of pi, because 4 times pi over 4 is pi over 4, minus 0. And pretty much what I'll get is 9 pi over 4. I hope you don't stop here, though. What else do I have to do? Yeah, multiply by 8. In other words, 18 pi is going to be my answer. Okay, so not too bad. That's our first one. Are we okay with that one? Let's try problem number 10 then. Let's see, do I have 10 on Desmos? I think I have one of them on, a couple of them on Desmos. I don't. Rats. All right. I'm not going to try and do that now. So, let's go back here. Problem number 10, we want to try and find one petal of r equals cosine of 5 theta. So one petal of that. How many petals would this have anyways? 5. All right, so 5. And I've kind of zoomed in on one of them. Now the graph of cosine is going to start out on the x-axis. Cosine is going to start out at its furthest extent, and then it's going to come back in here. So all the way to here. The question is, how long does it take before this point is going to make its way back to the origin? Well, think of it this way. We've got cosine of 5 theta. It gets back to the origin when the radius is what? 0. Yeah, 0. 0. Well, when does that happen? What angle do you take the cosine of to get 0? Pi over 2. So basically, 5 theta equals pi over 2, or theta equals pi over 10. And in general, it's going to be theta divided by 2n, much like it was for our sine. Although sine was giving us kind of a different point. All right, so let's do that. Let's integrate from 0 to pi over 10. Integral from 0 to pi over 10 of cosine of 5 theta squared d theta. Oh, and I need a 1/2 out in front here, right? Because that's part of my formula. Your turn to use the power reduction formula. 0 to pi over 10. I'll give you a hint. It's something over 2. I'm so generous. I'll give you another hint. You should have a d theta. Woohoo! On a roll. I am. My generosity amazes me. It's a 10. Where are you looking? Yeah, you're bad. I think it might have been a little dust on the lens. It was obscuring things. All right. So it's going to be a 1 and a cosine. Now this angle gets doubled. Cosine of 10 theta. But what sign goes in between them? I didn't hear you. It's going to be a plus. So this 2 comes out in front. I have 1/4 the integral from 0 to pi over 10 of 1 plus cosine of 10 theta. Now it's just a matter of finding a couple antiderivatives. I'll split the work with you. I'll do the first one. That's theta. You do the second one. All right. Plus got it, Slav? Plus what? Anyone? Yep. Sine of 10 theta over 10. If you need to slow down and take time to do a U substitution, that's fine. My trick is I always think of it this way. If I was differentiating this, I'd end up multiplying by 10. But since I'm integrating it, I divide by 10. Because integration is the opposite of differentiation. So that's where I get the divide by 10. And I know it's going to be a cosine or or integral of cosine is sine, or sometimes if you have integral of sine, you end up with negative cosine, etc. But I just look at it and say, well, if I differentiate this, do I get the right sign? Yeah, derivative of sine is cosine. I don't have to change the sign in this direction. So we're okay. 1/4 pi over 10 plus, that'd be sine of pi over 10 minus 0. And this term here is 0. That one disappears. So I'm just left with pi over 40. And that's almost correct. Multiply by 2. Pi over 40 times 2 is pi over 20. You're making me nervous. What? Okay, good. Yeah, I think that's all that they asked for, is one pedal. Yeah, no, it's a good question, but yeah, they asked for one pedal. So if they asked for 5 pedals, then we would take the final answer here and multiply it by 10, because there's 10 half pedals in our drawing. All right, good questions, gentlemen. Thank you. Anything else on that one? Okay. move up to problem number 26. So let me ditch those and move to problem number 26. Again, you've got a couple cardioids. Let me zoom out a little bit. Want to try and find the area bounded between these two cardioids. Now, that's going to pose yet a different challenge. The area bounded between these two cardioids, I don't know. Do you want them same color? Would that help out? No? Okay. Let's make blue. Is that better? No? You like orange? Okay, we like orange. All right, there we go. Keep everyone happy. So we want to find the area bound between these. Now, it looks like these things are symmetric, right? So if I found an interval for this one little region here, then I could times it by 2 and then by 2 again. Basically times this by 4 and I should be okay. So let's figure out where these things meet and how they meet and what our limits of integration should be. Yes? I think they just want, tell you what, I'm going to play my best card here. Let's move this down. What they want is this region here. Yeah. Ooh, ah. And this is kind of cool because it illustrates how this is going to be done. You're going to sweep out the area. And let's zoom in here a little bit for full dramatic effect. That's the wrong one. Down here. There you go. It's going to be swept out like that. So we're going to have to figure out what are going to be our limits of integration to get that little interval. And then if we double it and double it again, then we should have the interval bound between both two curves. All right, so that's our attack plan. You could actually probably take a reasonable guess at this, and you'd probably be right in terms of where they're going to meet. But let me just kind of show you what you might have to do in certain problems anyways. So this is problem, what was it, 28? 28, no, 26. So we had r equals, you know, I hate it when they don't distribute that, 3 plus 3 sine of theta. And the other one was 3 minus 3 sine of theta. If we want to know where these things are equal, well, we can set them equal to each other. It's going to be 3 plus 3 sine of theta equals 3 minus 3 sine of theta. Right away, you can subtract 3 from both sides, get rid of that. Then I'll add 3 sine of theta to both sides. And I end up with 6 sine of theta equals 0, or in other words, sine of theta equals 0. So sine of theta equals 0, where am I going to get a solution for that? Yeah, sine of theta equals 0, theta equals 0. So that's going to be one of our limits. It's going to be one point where they intersect. Should get a couple of other ones. Let me see here. I need this one here. Where's that going to happen? So 0 is 1 point. What did I do earlier? Yeah. Powers. Let's see. There, power 2. So I got 0 is 1 point. Got to get one more. And I got to justify that second limit here for us. Pi r2. Oh. Yeah, so the second point is going to be when the radius is 0. When the radius comes back down here to the origin. So that point we can solve for as well. Let me go back to this. If the radius is 0 in these equations, I get 0 equals 3, let me use this one, minus 3 sine of theta. In other words, 3 sine of theta equals 3, or sine of theta equals 1. That means theta is the inverse sine of 1, or pi over 2. So that's my other limit of integration. The last part of this then is to put in our limits of integration and integrate this formula. A good question is, which one of these should I choose? Now this is actually on your graph right here. Which one of these is which? I've got two functions. I got r equals 3 minus 3 sine of theta, and r equals 3 plus 3 sine of theta. So which one's the top function? Yeah, so this one that I want to use here is going to be facing down. So it's going to be the minus. Is that going to be right? Let me just double check that. I'll think through this one. At 270 degrees, no. No, it's going to be this one. That one's going to be the one that faces down. Is that right? Let's just double check that. It's getting late at night for your instructor too. So, yeah, the top one, the one that we want, yeah, it's going to be this one here. So 3 minus 3 sine of theta. All right, so that's the one we're going to want to put on our integral. To be honest, I think it would work out okay with either one, but I definitely want to have the right one there. So let's integrate. It's going to be 1/2 times integral from 0 to pi over 2 of 3 minus 3 sine of theta squared d theta. Yay, so we get to have a little fun integrating. Yeah, listen to the crowd go wild. All right, if I factor out the 3, yeah, you have to FOIL it. Please do not give me 9 minus 9 sine squared of theta. Please don't do that. All right. I'm going to factor out the 3, so it's going to be 3 squared times 1 minus sine of theta squared d theta. So I factored out the 3, and then you had to square it to bring it outside the parentheses. So this is 9/2 times the integral from 0 to pi over 2 of 1 minus 2 sine of theta plus sine squared of theta d theta. And you should start to see kind of a familiar trick in these things, and that is in order to integrate this thing, we need to use the power reduction formula. 1 plus sine squared is what? If it was 1 minus sine squared, we'd be in great shape, right? But we're not in great shape. But it's good to look at it. I mean, I would have no problem doing something like that, but it just doesn't fit here. So 9/2 times the integral from 0 to pi over 2 of 1 minus 2 sine of theta plus 1 minus cosine of 2 theta over 2. Now this term is a 1/2 that I can add to here. So it's going to give me 9/2, the integral from 0 to pi over 2 of 3/2 minus 2 sine of theta minus 1/2 times the cosine of 2 theta. All right, need to give myself a little bit more room. Nine halves times the antiderivative, which would be 3/2 theta, plus 2 cosine of theta, minus 1/4 sine of 2 theta. All right, I think that looks pretty good. Okay, so let's continue. 9/2 times plugging in 3 pi over 2, or plugging in pi over 2, I'd end up with 3 pi over 4. Cosine at pi over 2 is going to be 0. 2 times pi over 2 is pi. Sine of that is also going to be 0, so 3 pi over 4. Minus 0 plus 2 minus 0. So at least the evaluation of this was merciful. 9 over 2 times 3 pi over 4 minus 2. Now I'd like to tell you that we're all done, but we're not. Why aren't we all done? I think by 4. Right, because we calculated the area of half of that figure. So times by 4. 4 times that's going to cancel, so I'll just end up with an 18 out in front. So it equals 18 times 3 pi over 4 minus 2. And you can distribute or not, whatever, it doesn't matter. I'm not really that worried about it. Just please remember to multiply by the pi or by the 4 when you're all done. That's not a big deal. That's like a 1-point thing if you forget that. The big thing is to find the area of that little portion there. Okay, one last one. Happens to be on your handout. It's problem number 38. So again, you have 2 figures that bound a region. These aren't graphed for you. We did play around with graphing things on your graphing calculator, so you can find those things, hopefully. Hopefully some of the tricks I've taught you will help out. Our 2 equations in this case are r equals 5 minus 3 cosine of theta, and no, 5 minus 3 sine of theta. Yeah, and then cosine of theta. 5 minus 3 cosine of theta. So once again, we're faced with trying to find an area in this region that's kind of a common region. Let me think about which one's going to be which. let's see, cosine so 0. That's going to have to be this one. So that's going to be your one region, and then here's going to be your other one. So the question is, where do these two things meet? What angle for theta? So just like the last one, we're going to have to start out by finding where they meet. And there's a little bit of a trick in this one, so let me help you out with that. As before, we're going to set these things equal to each other. So this is problem 38. 5 minus 3 sine of theta equals 5 minus 3 cosine of theta. Unfortunately, you're not going to be able to factor and set something equal to 0. We can get rid of the 5s right away. We can also divide out by the 3 and get sine of theta equals cosine of theta. The trick in this that I teach my trig students is if you divide both sides by cosine of theta, then you get something at least reasonable on the right-hand side, and that is a 1. On the left-hand side, you get a tangent. Does anyone remember where the tangent of theta is equal to 1? Yep. Good job. Pi over 4, or 180 degrees away from that would be, or pi away from that would be 5 pi over 4. So there's two places, pi over 4 and 5 pi over 4. So that's what we're going to do for our limits of integration. So let's shut this off and take a look at this graph. So let's zoom out a little bit. And we're going to integrate from pi over 4 to 5 pi over 4. So ready, set, go. All right. I'm sure the audio almost picked that up. That was good. Thank you. All right. So there's what it's going to look like. We're going to do this halfway around and then double it. You have to be careful about going outside of this, because once you go outside of this, you've left this curve and you'd be on this next curve. So you can't just integrate from 0 to 2 pi or something like that. You have to be careful about your limits of integration. So let's see. Let's set up our integral. We're going to integrate 1/2 of 5 minus 3 sine of theta squared. And our limits of integration are going to be between pi over 4 and 5 pi over 4. So let me click over here like that. And I want this d theta. When you square these things out, boy, I hope that at this point you can kind of square these things out in your head. The trick that I use for myself is I know the end terms are going to get squared, so we'll do that. That's going to be pretty easy for the first one. It's going to be 25, and then over here I'm going to have it with 9 sine squared theta. The middle term is just going to be twice the product of these things, so I always borrow this 2. 2 times 5 times 3, that's going to be 30, so minus 30 sine of theta. If you're not comfortable with that, just write it off to the side. 5 minus 3 sine of theta times 5 minus 3 sine of theta. I think by the end of the homework, you'll have this substitution memorized again, right? The double angle formula seems to come up quite an awful lot. So it's going to be 1/2 the integral from pi over 4 to 5 pi over 4, 25 minus 30 sine of theta, plus, let's call it 9/2 times 1 minus sine of 2 theta, or minus cosine of 2 theta. That figures that off. And then more d theta. 9 halves times 1 is going to be 9 halves. Let's call that 50 halves, right? That's 50 over 2 is the same thing as 25. So 50 halves plus 9 halves gives me 59 halves. Pi over 4, 5 pi over 4, 59 over 2, minus 30 sine of theta, minus 9 halves cosine of 2 theta, d theta. Now let's get some antiderivatives. Pi over 4, 5 pi over 4, 59 over 2 theta. Be plus, right? Plus 30 cosine of theta. The derivative of cosine is negative sine. Minus 9 over 4 times the sine of 2 theta. D theta? No, we don't need d theta anymore. I think we're pretty good there. Okay. The rest of this is looking pretty ugly, isn't it? Boy. Oh, look at the time. It's time to go for homework. Oh, man. I don't have... I've got to have this one done out someplace. There. Oh, here we go. All right. Oh. Equals 59 pi over 2 minus 30 square roots of 2. Happy Thanksgiving. All right, I might have left out 1 or 2 steps in there. Yeah. There actually is a little bit more that I have to finish up with you, and there's one formula for arc length in polar coordinates that we haven't covered yet, but I'll have to take care of that next time. Are you like massively curious about the details here? I can fill them in. Happy ending. Okay, good deal. All right, for homework. Try 1 through 29. And we'll just go mercifully 35 and 37 for right now. Yes, sir.
I was just wondering when we have to add 180 degrees to the limits of integration. Like, we had pi over 4 and we had to add 180 to it.
Oh, that comes from the solution of the tangent equation here. There's 2 places that the tangent's equal to 1. They're both at multiples of 45 degrees. But one of them's going to be in the 3rd quadrant, and one of them's going to be in the 1st quadrant. Yeah. Because remember, you might remember way back in your trig class, all students take calculus. So all of your trig functions are positive here. Tangent and its reciprocal are positive here. So that's where you're going to have tangent is positive here at 1, or at 45 it'll be 1, and at 5 pi over 4 it's also going to be 1. Okay? It's square root of r squared plus r prime squared, or f of theta squared plus f prime of theta squared, where f of theta is, whatever r is.
So when you go to sub theta back into that, you use the pi over 4 or the 5 pi over 4?
Yeah, there's a fair amount of work in simplifying that. I mean, some of them simplify okay, but it's a pain.